Hi. In the previous video, we discussed Maclaurin's series of a polynomial function. However, I don't know if you noticed it, but we were doing the expansion of this function at 0, which made all the calculations fairly easy. However, what about other points? Can we do a similar expansion of a series around some other point? And the answer to that is Taylor series of a polynomial function. And look, how do we get to this result? Let's start with the exercise we solved during a previous video. Right? We've actually shown that using Maclaurin times series, we will get exactly the same function. However, let's go one step beyond what we did before. Let's just say that x, in our case, is some x0 plus delta, where x0 is a chosen value. Like a constant. Yeah, this is the given value of x that we have established. Now, what is delta in this context? This is deviation from x0, right? Delta can be both positive or negative, so it can be either above or below x0, right? And so what do we get here? Here, basically, we will get some expansion, and we will get some value of x plus or minus this delta, if delta is negative, right? Okay, knowing this, we can do the same exercise again, but a little bit different. Okay, let's start by substitution. So now, our f of x is equal to 2 plus 4. Instead of x, I'm writing x0 plus delta plus 3x0 plus delta squared. Okay, now, if I'm going to differentiate this function with respect to x, is the same as I would be differentiating the function with respect to this expression, right? So what is going to happen here? First derivative, this is going to be gone. It's going to be 4 plus 6x0 plus delta, right? If I'm going to do differentiation for the second time, I'm going to get that this is just 6. Okay, now let's consider one thing. We said that x0 is some given constant, right? So if x0 is a constant here, the thing that might be changing is delta, which means the delta, if it goes up, we're getting above, further and further from x0, or if it gets really, really small, but in a sense that it's getting very negative, we're going away from x in the opposite direction, right? So maybe, just maybe, instead of writing this function, as a function of x, we can write a similar function. We can write identical function, but not written in terms of x, but rather delta. Because look, if this is constant, the only change in x comes from change in delta. Right? So let's try. Let's say we've got a function g. And this is the function of delta. Right? How can I write it? Well, actually, exactly in the same form. remember that this is a constant, this is g. However, we should notice that this is the same as f of x. Okay, what will happen if I'm going to differentiate it? Look, if I'm going to differentiate it first time with respect to delta, this is gone, and now this part is gone. This part is gone. All we have is the coefficient on delta, which is 4, and then here we need to use the chain rule. As you see, what we got is simply first derivative of f of x. And again, if I'm going to differentiate it for the second time, this is gone, this part gone, only the coefficient on delta, which is 6. And again, this is the second derivative of f. Okay, so now look, we can, for this function, we can easily use Maclaurin's formula and do the expansion around 0. Okay, what will we get? The g of delta is equal with the formula. So this will be g of 0 over 0 factorial plus g of 0 prime over 1 factorial times delta, right? And plus g piece of 0 over 2 factorial delta squared. Okay, so now that we've actually used Maclaurin's formula to expand the g function, let's notice, let's leave this function and leave what we assumed at the very beginning. Now, okay, so let's notice a couple of things. First, when delta is equal to 0, right? What do we get? X must be equal to x0, right? Moreover, because f of x is the same function as g of delta for the case delta equal to 0. What will we have? g0 is equal to f of x, right? G prime of 0 is equal to f prime of x. And finally, if g piece of 0 is equal to f piece of x 0. Again, so look, we have actually came quite a long way. Let's just notice one additional thing. Look, out of this expression, we know that x is equal to x0 plus delta. Right, but if x is equal to x0 plus delta, then this tells us that delta must be equal to x minus x0. And look, if this is the case, we will find a very, very nice way to write this function in terms of any x0. Why? Look, all I need to do is to take the Maclaurin formula I've just used, so the one that you see over here, and start replacing it. First, instead of g of delta, I can now write f of x. Instead of g of 0, I can write f of x0, right? Divided by 0 factorial plus. Now, instead of g prime of 0, I can write f prime of x0 over 1 factorial. And now, instead of delta, I write x minus delta. So, I hope you can see now that the next component is going to be fds of x0 over 2 factorial times x0, x minus x0 squared. Okay, this has shown, now we have shown that we can go from the function that we had at the beginning, expand it at any x using this formula, and we should get the same function. Okay, let's check if this actually works. Okay, so let's check it on our example. Okay, let's just say that I'm choosing x0 to be any number, right? So I'm going to leave it as x0. So now our function becomes 2 plus 4x0 plus 3x0 squared. First derivative is equal to 4 plus 6x0, and second derivative is just 6, right? Now, let's apply the formula and let's see what we're gonna get, okay? So, this is gonna be 2 plus 4x0 plus 3x0 squared over 0 factorial, which is 1. This is gonna be pretty easy to copy. Then we've got plus f of x0, so this is 4 plus 6x0, f prime of x0 over 1 factorial times x minus x0. And finally, we are having 6 over 2 factorial times x minus x0 squared. Okay, let's calculate. Well, the first part is not changing, right? We're dividing by 1, so it's 2 plus 4x0 plus 3x0 squared. Then we need to, here we again divide by 1. So I just need to multiply each of these components by what is up front. So we get that this is plus 4x plus 6x0x and 4x plus 6x0x, and now minus 4x0 and minus 6x0 squared. Okay, here we will have 3 plus 3, right? 3 times x squared, right? Minus 6x0x, and finally plus 3x0 squared. Okay, now let's see if this expression will simplify, right? I see 4x0s here with plus, here I see 4x0 with minus. Here I have 3 here I have plus 3x0 squared. Here I have and minus 6x0 squared. Okay, finally, here I have plus 6x0x minus 6x0x. And this is it. This is the solution, right? We got that using this formula, the Taylor formula, we're having 2 plus 4x plus 3x squared. So, again, we started with this function, we used the expansion, and we got the correct result. Okay, so finally, we can write down Taylor series of a polynomial function. And look, it's going to resemble Maclaurin series. The only difference are going to be deviation. So we're going to have f of 0 over 0 factorial. Here we could have x minus x0 to the power of 0. Of course, we don't need this. Then we would have f prime of 0 over 1. Of x0 over here and here. x0 over 1 factorial times x minus x0. Of course, here we could put to the power of 1. And then f piece of x0 over 2 factorial is equal to x minus x0 squared. The next component would be the third derivative, evaluated at then 0 over 3 factorials times x minus x0 cubed plus, of course, we go on like this until we get the last element, which is nth derivative of function f evaluated at point x0 divided by n factorial times x minus x0 to the power of n. And this formula is of course known as a Taylor series of a polynomial function. Okay, I realize this is still pretty abstract. Okay, so let's just summarize what we have accomplished. Look, with Maclaurin's series of a polynomial function, we figured out a way to take a polynomial function, then choose a specific point, 0, and based on evaluation of the derivatives at this specific point, so at 0, we could rewrite the polynomial into a different series. What is the new thing that we've introduced now? Well, we are moving away from 0. Look, before we had 0 over here. Look, now if I would replace x0 with 0, we would just get Maclaurin's formula. So definitely, Taylor series is an extension of this formula. It's a generalization of Maclaurin's formula. So look, what we know how to do now is to take any polynomial function and use any point to write an expansion, a series that will give us exactly the same function. Okay, I know that this is still very abstract, but this technique will allow us to make a lot of calculations very, very simple. What do I mean by that? Is that at this moment, what we are actually doing is we are trying to take one function, some polynomial function, and we are are trying to rewrite it in a different form. Which, of course, is interesting, but not very useful. However, in the next video, we're going to move one step forward. And as it turns out, that Taylor expansion can be used to approximate not only polynomial function, but basically any function with some minor requirements that we want. And this is going to be a topic of our next video.